Welcome everyone to this week's edition of HoloTube, and we are very happy to have Sasha Grozdanov from the University of Ljubljana tell us about the bounds on transport from Univalence. So the screen is yours.
The screen is mine. Thank you, Matthias. Thanks to all of the organizers for organizing this, and it's been sort of an ongoing, very nice seminar series on various things that interest us. So it's nice to be a part. Also on the other side of the screen, I suppose. And so I guess we can start. There's a fairly small group, so it should be manageable. People should just ask questions. So the title of my talk today is Bounds on Transport from Univalence. All right, so what do I want to do? So what is the main motivation? So the main motivation for what I'm trying to do is to develop some kind of precise analytic understanding of various aspects of transport. So we know that, this is a kind of an audience to which I don't have to especially introduce the value of studying transport in, strongly interacting quantum field theories, etc. So, we know that this kind of transport holography / hydrodynamic description of transport has been very, very valuable. It's good for describing fluids, gases. It's also used in theory of electrons, in graphene. People use these kinds of simulations to talk about neutron plasmas, to talk about neutron stars, and they also talk about, one of these sort of things that is of highest interest to this community, which is quark gluon plasma. Okay, so it depends on exactly what part of the community you come from, but these are the sort of, physical things that motivate the kind of studies that we do. So there are sort of three statements that I'm going to address today. Oops. The first statement that sort of keeps appearing, all over the place is that hydrodynamics as an effective description works unreasonably well. So I will not say much about this, but I will just sort of review what from my point of view of my recent work, what I think that we have learned about this question, which is sort of broad, but from one particular point of view that I've been sort of interested in. Then the second sort of aspect of the things that I have been interested in is this connection between the mess of quantum chaos. Quantum field theory has some kind of mess, something is going on inside, and it gives rise to some emergent dynamics, which is macroscopic. All right, so I would like to, understand how precisely this happens. So I would just very briefly review this phenomenon of pole skipping, which I think is also sort of familiar to at least some, subset of some, many of you have worked on this. So this is sort of familiar. And then the main part of what I want to talk about today is, about bounds. So this is another thing that's been sort of huge interest to this community and communities before. This is, a long-standing debate of the question of, are these hydrodynamic observables that we talk about, like diffusion and the speed of sound, are they bounded in some way? All right. So what I'm going to show you today is a new method for finding exact and rigorous bounds on transport, given some precise set of analyticity conditions. So what I will not talk about today are universal bounds on, on diffusion or the speed of sound that are true generically for quantum field theories. This is not the goal today. This will be the goal of my future exploration. But what I want to do today is introduce new methods whereby you can actually make such statements, okay? Given some exact class of something where you know what exactly it is that you're talking about, okay? So, all right, so in a very, very brief one sort of introductory slide to hydrodynamics, what is hydrodynamics? Well, we know by now that hydrodynamics is an effective theory of various quantum field theories. It arises in the low energy limit, okay? Somehow defined. And we know how to deal with this. We know that this has to be done in the language of Schwinger-Keldysh effective field theory. So for the purposes of what I'm going to do today, these details will not be so important. All you sort of need to remember is that hydrodynamics describes the long time and the long distance evolution of globally conserved operators. So, you can have conserved energy momentum, then you have a conserved energy momentum tensor. You can have conserved Noether charges, then you will have some conserved Noether current, something like this. For example, for baryon number or something else, whatever is of interest to your particular system. And then what we know now is also, if you have some global symmetries, which are higher form symmetries, like in magnetohydrodynamics, then you also need to include all of these. So in principle, what you do, you find all of your conserved operators, you write them down, and then you perform some gradient expansion, which is a tensorial expansion of these variables, of these conserved operators in terms of some hydrodynamic fields, right, which you pick to parameterize your theory. This is very much an effective field theory approach. So you write this down in the most generic way, and you can, equip each term with an unknown coefficient. Now, these unknown coefficients are either called the equation of, or either called, some kind of thermodynamic quantities which are related by the equation of state, or transport coefficients. Of course, you cannot compute any of these from an effective theory. You need some kind of microscopic framework in order to be able to set these different coefficients, given, some specific theory that you're interested in, okay? And for, all of what I'm going to say today, I'm only going to be talking about hydrodynamics as a, as an infinite order gradient expansion, without talking about any kind of loops or any kind of 1 over n effects or long time tails, non-analyticities, stochasticities, blah, 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 blah. None of this will be addressed today, okay? All right, that's the sort of disclaimer. And of course, on my last slide, I will say that this is what we need to do in the future, as we always say. Okay, good. So we're done with that. So let's just stick to hydrodynamic theory as a gradient expansion. All right, so what I can do here more concretely, I can write, let's say, I can forget about charges. So I can write my T mu nu, the energy momentum tensor, in an infinite series. All right, so I can write the sum over small n, where each n counts the number of derivatives acting on the hydrodynamic fields, like the velocity and the temperature. And at each order, I write all possible coefficients that are linearly independent. This is, of course, a very difficult task. We don't know how to do this to high orders. But what we do know is that if you have such an expansion, and then you plug it into your equations of motion, which here is the conservation of the energy momentum tensor, then you can make some predictions about how such systems would and should behave. So the easiest thing to do is to take your fields and you decompose them in terms of Fourier modes. You plug this all in, and then it's easy to see that the solution to this now algebraic set of equations will be some set of solutions in terms of omega expressed as a power series in Q. So omega for me is the frequency. Q is, in this case, let's just think of it as the absolute value of the vector momentum, all right? So this will be important. Momentum is, of course, a vector. So this is sort of defined here. So the point here is that this omega as a function of Q is an infinite series, all right? Now, what is hydrodynamics, right? So in order to have sort of a sensible expansion in this sense, what sort of the input is that you expect these derivatives to be small, all right? The derivatives of the field should be small. So what does this translate to in momentum? So, well, it translates to the fact that your frequency and your momentum Q should be small compared to some dimensionful quantity, which characterizes equilibrium. Okay, so equilibrium in position space is typically characterized by not having derivatives, although of course there are solutions to hydrodynamic equations which are not really equilibrium from this point of view. But I will be talking about these sort of things that are nicely sort of fluctuating around thermal equilibrium. So all right, so then one has, of course, different types of these solutions. So these solutions are called dispersion relations, and these dispersion relations can be, in the simplest cases, either they can be diffusive or they can be sound. So if something is diffusive, such as, for example, for transverse momentum or something like this, then you have omega as a function of Q, which is imaginary. So you have an imaginary part minus ID times Q squared, and this D is the diffusion constant, which depends on the microscopic input. It depends on thermodynamics and it depends on the microscopic transport coefficients. All right, so it's purely imaginary. Therefore, it's purely damped. So for sound, which is a propagating mode, you have a real part. This is the speed of sound, and then you have an imaginary part, which is sort of the attenuating part. All right. Now, of course, in principle, these things do not truncate here. This is just the first order Navier-Stokes hydrodynamics. This series continues, as I told you here. Okay. So what I'm going to do today is to talk to you about these things as, in full. I want to tell you sort of, things about the analytic properties of these infinite dispersion relations, which are infinite series, and in principle, they can be resummed into some function, all right? And this function is, it's a solution to the modes, to the spectrum of your quantum field theory. So this is my very brief introduction. Now, I'm going to go through these 3 steps. I'm going to briefly review and tell you maybe a few new things about complex spectral curves and convergence. I think this is mostly, at least the old story is mostly well known to this audience. Then I will also tell you something new, something that you also know about the business of pole skipping. I will not tell you anything new about pole skipping today. And then finally, I will sort of use these two pieces of information and introduce some new tools from complex analysis to discuss exact bounds on these things that I have sort of introduced here. I want to talk about, specific bounds on these coefficients like D and Vs and gamma and all of this stuff, all right? That's the goal. So before I start, does anyone have any sort of question or comment about this? Okay, great. All right, very good. So let's start with a sort of brief, overview of this business of convergence of the series and the complex spectral curves. All right. So what we sort of introduced in this PRL and then in subsequent papers where this was better understood through various papers was that these hydrodynamic dispersion relations that I introduced here, these omega as a function of Q, they are best understood in the context of what are called spectral curves, complex spectral curves. So, at the end of the day, when you have sort of either from field theory or from holography, you have computed some equation which you need to solve in the end, you can think of this as some equation P of momentum Q squared omega having to be equal to 0, okay? So what you need to do is, you need to consider this in the complexified space of frequency and momentum, all right? And sometimes for purposes of dimensionless quantities, I will be normalizing these with 2 pi d, okay? This is the usual convention. So, all right, let's see. So if you just do first order hydrodynamics, forget about holography, just do first order hydrodynamics, what you find is this complex spectral curves, let's call it P1, which has this form. So first of all, it factorizes into 2 distinct pieces. So this is just, neutral, relativistic, rotationally invariant hydrodynamics. So there's a diffusive piece and there's a sound piece, okay? And then of course, once you start adding higher derivative corrections, this gets more and more and more and more complicated. And this need not actually be a polynomial equation. It can, if you compute it from holography, in principle, it can look much more complicated, all right? So it's, some very complicated function. This is actually the function that gives you the spectrum of quasi-normal modes, okay? For those of you who work on holography, this is exactly what this is. So normally, of course, you cannot solve such a thing. So what do you do with such a thing? Well, what you do is you try to perform a local analysis. And what we showed in these papers was that, through this technology of the Puiseux theorem and the Puiseux series, what you can find, you can show that generically hydrodynamic series of the type that I'm describing will be convergent series, okay? So basically, there is the classification of these critical points, thanks to Puiseux and other algebraic geometers who have been working on such things for centuries, essentially since Newton, or maybe even before. So what you can show is that these series will, so you can form local series around what are called critical points. So a critical point is something that solves the equation normally, right? Of course. So you have Q star omega star has to be equal to 0. And then let's say your first derivative actually can still be 0, then this is a critical point of higher order. And, in principle, you can only have pth derivative, which is non-zero, all right? So for such a thing, what you find by this theorem is p branches of such a series around this particular critical point. Now, the key here is that actually convergence of such series is guaranteed. So the convergence of such series always exists, at least until the next nearest non-trivial other critical point, okay? Now, these other critical points, as long as they're non-trivial, there's no factorization on, at those critical points, will give you branch points, all right? So they will give you branch points and they will give you branch cuts in the dispersion relation, omega as a function of Q. And so these, you find some series, then you can sort of understand whether the series, where exactly the radius of convergence is. For example, you can construct a Newton polygon at these various places, at these various complex critical points. Now, I think regarding this statement, there has been sort of some confusion or misunderstanding. I don't exactly know why, but what can happen, for example, is that you have a critical point, because what you're computing are critical points of the full spectral curve. Okay, then you find your series. There can be sort of anomalous cases where, for example, this thing converges past the nearest critical point. So actually, such cases were discussed in our paper. What we called those cases was level touching as opposed to level crossing. So what actually we showed now, and this is a paper that's coming out either at the end of this week or next week, where we're mainly interested in computing these critical points and radius of convergence at finite coupling, there's actually a very simple diagnostic tool to understand what will happen at this next critical point. So what you can do is the following thing. Now, you can use something called the Darboux theorem, which I think people know well in asymptotic analysis, but maybe in this context, it has not been known before. So what you can do is actually, you can compute the exponent at the, the Puiseux exponent at the next critical point by just looking at the series coefficients of the series around your critical point where you're computing your series, okay? So this is the sort of an equation. I will not discuss any details of this, but essentially, imagine that you have a series in t around 0, all right? And you know the coefficients of the series, which you call an. So then this means that, this function will behave as, something like this. It will have a regular part r of t, and it will have some singularity like this with some exponent nu, okay? So clearly, if this is a critical point of order 2, then this nu should be -1/2, okay? It's a square root. So you can check what this nu has to be, and you can actually compute it in something that looks like, it's like a convergence test or ratio test or something like this. So you can just directly compute this exponent from the series coefficients, and then you don't have to worry. You don't have to worry, and is it level crossing? Is it level touching? You can just see exactly what the coefficient is. So, I think we sort of, some of these things were misunderstood in our previous papers, and hopefully this paper this week will sort of sort this out so people don't have to worry about this anymore. Anyway, so I don't want to discuss this today too much. What I want to just make sort of these generic statements is that these hydrodynamic series, what we showed, were generically Puiseux series, all right? So they're Puiseux series around omega equals to 0, q equals to 0, because hydrodynamic series are gapless modes. And what they are convergent series. So for shear modes, they're actually p equals to 1 series. So this critical point here at 0, 0 is order 1, which means that a diffusive series is a Taylor series. It's a Taylor series in momentum vector squared, all right? So this is a Taylor series to the power of n. Now, sound series are actually Puiseux series of order 2. So this means that they come in 2 branches. Well, we know that there's this plus minus business, right? So all of the structure and what, which term is imaginary, what has a plus, what has a minus, and what coefficients are real and what not, everything is determined directly by this Puiseux theorem. So these sound modes are Puiseux series in order 2 in q squared to the n over 2. Okay, and this is what they are. And for example, one can then, in a holographic model, study precisely what this radius of convergence is. And this is some new plot, which is going to appear in this paper this week. This is the radius of convergence for n equals to 4 super Young mills, computed at finite coupling, all right? It's done in this way where you compute things perturbatively. So this blue curve is the perturbative solution. So what is actually very surprising about this is that as you tune the coupling away from infinite coupling, so this gamma being equal to 0 is infinite coupling. Then you tune the coupling to be smaller. And actually what is surprising is that first the radius of convergence is improved, okay? And then, okay, eventually you can't trust this perturbative calculation anymore. So what we do is we perform this resummation, which people have complained about. And it's somewhat ad hoc. You can complain, you cannot complain. What I think this paper also does is, to some extent, maybe makes this clear and shows that actually, even in cases where the spectrum is non-perturbative, you can actually, in some cases, compute critical points perturbatively. So in some cases, it happens that these critical points, the perturbative calculation of critical points, knows about the collision with a non-perturbative mode and so on. So this is not the point of the talk today. This is just to say that, this has been done and this will appear this week. But the point somehow here is that these dispersion relations have a large radius of convergence. And, as you tune the coupling away from infinite coupling, at first it actually improves. So it's kind of piecewise continuous. And only then it sort of transitioned to what you would naively expect in the sense of hydrodynamics becoming worse and worse as you go towards weaker and weaker coupling. Okay. And this is the result computed perturbatively for the shear and sound mode radii of convergence. Okay, so as I said, I will not discuss this too much. What I really want you to take from this is that hydrodynamic series are convergent, so they have a finite radius of convergence. So this means that in some disk at least they are analytic. All right, and then you can use holography to compute this radius of convergence. What then generically happens from this Puiseux analysis, the analysis of critical points, which you can now verify with this Darboux theorem, etc., etc. The point is that these things, these dispersion relations, are generically extremely complicated Riemann surfaces. All right, so they have some disk where they converge. This is this green disk. This is the result for n equals to 4 super Young-Mills in the diffusive channel, but it doesn't matter. So beyond this, it's some complicated Riemann surface. And you can actually access, of course, these other branches through analytic continuation and all of this kind of business. So this is the simplest analytic structure of dispersion relations. Okay. Now, sort of to summarize what I wanted to say in this first part, also in the context of what people talk about when they really talk about unreasonable effectiveness of hydrodynamics, typically what they mean is that hydro works for large derivatives. Okay. So what I think also this analysis that we've been doing and other people have been doing shows is that indeed, actually at strong coupling, we see that these hydrodynamic approximations to the full QFT actually work very well. Not only when they have sort of large derivatives, but from the point of view of momentum space, one can make this fairly precise, right? So in terms of momentum space, what we observe is that these radii of convergence are very large. They're on the order of Q over T being order 10. And this actually seems to work even when one sort of moves away from infinite coupling, at least for some small region towards finite coupling. Okay, so all right. What I wanted to say here, therefore, was that basically these hydrodynamic dispersion relations have orders of magnitude larger radii of convergence than what you would naively expect, which is roughly that this Q over T should be very small. Okay, so what I like to view this as is one precise incarnation of this unreasonable effectiveness of hydrodynamics. And it is, precise from the point of view that we sort of, analytically know exactly what we're doing here. All right, so this is the first part. Now, in the second part, what I want to do is sort of relate this business of hydrodynamics, which is, emergent collective dynamics, to quantum chaos. All right, so are there any questions or comments about this?
Hey, Sasho, hi.
Hey, Umut, yes?
Yeah, I have a question. So the figure that is going to appear next week, how do you compute this?
Which one?
The one that goes up and down.
So this thing?
Yeah, this is holography, right? Is that
this is holography? Yeah, this is
Gauss-Bonnet, right?
No, this is type 2b supergravity.
Okay, I see.
This is this Riemann to the fourth business.
Okay, good. Yeah, so that's what I wanted to ask. Yeah, okay, perfect. And this fact that it goes up first and then goes down, is it? Do you see any kind of universality there? Is there any reason for that?
It's that. So what happens when you do this non-perturbative resummation? Let's put it in quotation marks. And actually, the same thing happens in Gauss-Bonnet. There's also this transition. So what happens is that at first, this radius of convergence, right, is determined by the collision of the hydrodynamic mode with the gapped modes. So if you imagine at infinite coupling, you just have the Christmas tree, and there's a collision between the hydro mode and the gapped mode somewhere in the complexified momentum space. And then eventually, so you have also then these modes on the imaginary axis, and they come closer and closer. This also happens for Reisner-Nordstrom or this kind of stuff. You have these extra modes, right? And so then eventually this takes over. So this non-perturbative mode eventually takes over. And so this transition occurs when it's a different mode that takes over the limitation of convergence. So you go from one mode to another.
Yeah, I understand that there should be some kind of non-analytic behavior when the modes collide, but I don't understand why it should go up. It could have been going down and then having some,
It could be. Yeah, so that was actually a surprise to us. We expected somehow naively, you would always think that, well, actually, hydrodynamics gets worse and worse as you make the coupling weaker. So you would expect, from the point of view of radius of convergence, that it will just get smaller. But this does not happen. And actually, so there's sort of, I didn't want to talk too much about this, but there's also a paper by Matteo Baggioli where he estimates the radius of convergence of some realistic fluids from, some estimates of what this business of the K gap. And there's also a paper by so various authors, Sharoshi, Meze, and collaborators, where they looked at the radius of convergence of diffusion in SYK chain. And there they can compute it non-perturbatively in the coupling. And they also see this kind of, piecewise somehow behavior. So qualitatively, this n equals to 4 summation gives the same kind of piecewise behavior as what they saw. So it seems that it's not a monotonic function.
Yeah, okay, thanks.
But somehow I cannot give you some deep physical understanding of why this should be.
Yeah, I understand, yeah.
Yeah, that's right. Thank you, that's a very good question, yeah.
Can I tag on to that question and ask,
yes, of course,
what exactly gamma is the inverse of? Do we know?
It's so it's proportional to 1 over 't Hooft coupling lambda to the minus to 3/2.
Mm-hmm.
Yeah, so it's this this business of Riemann zeta function of 3 divided by 8 factorial lambda to the 3/2. This standard supergravity coupling.
Okay, thank you.
Yeah, good. Okay, great, thanks. So they converge and they have nice analyticity properties that are sort of better than, what I had expected naively before, I would say. All right, so good. So now extra property of this stuff, right? Through holography, actually, we were able to access these, fascinating world of quantum chaos. So what is quantum chaos? Well, let's start with classical chaos. So classical chaos is, typically synonymous with extreme sensitivity to initial condition, right? You have some kind of trajectory in phase space, it diverges exponentially, and it's characterized in time by this Lyapunov exponent lambda L, and it has some, let's say, cone-like spatial propagation that's characterized by VB, which is the butterfly velocity. Now, we ask, of course, what is the quantum analog of this behavior? Now, this is, quantum characterization of quantum chaos is impossible. This has not been done. We know, something about it, but for example, it's very difficult to define, the question of what are the phases of quantum chaos. All of this kind of stuff is not particularly well understood at all, actually. So what has transpired in recent years is that one can compute this kind of exponential growth and associate it with quantum chaos by looking at OTOCs, all right? So OTOCs have exponential growth for these large N holographic theories, at least, and one can associate this growth to the quantum Lyapunov exponent lambda L and VB, the butterfly velocity. So I don't want to say more about this, but just to sort of, remind you that there's a sort of a beautiful result regarding this exponential growth that was derived by Maldacena, Schenker, and Stanford. And it's an upper bound, it's an exact upper bound on lambda L, supposedly in all quantum field theories. So there's an upper bound that's 2 pi t over h bar. And we know that this is saturated by holographic models, which have a classical holographic dual, all right? So this is great. It's an exact bound, and this is exactly the kind of thing that we like, and we would, we would want also for other things. I should also sort of alert you here that there are various systems which are quantum chaotic, like quantum spin chains that have a finite local number of that have a finite local Hilbert space, and such things do not have exponential growth of the OTOC. So what actually we were able to prove with this group in Ljubljana before I was here was that the chaos in such systems always spreads polynomially. And it spreads polynomially with the rate that's at most t to the 3 times d, where d is a number of spatial dimensions. So, you can sort of think of exponential chaos and weak quantum chaos, which is polynomial, as 2 different phases of chaos. And they have sort of analogous bounds, okay? There's an exact bound on the growth rate of how fast this chaos can propagate. Now, what is pole skipping? So pole skipping, as most of you know, is a precise analytic connection between these low energy hydrodynamic dispersion relations that I'm talking about and quantum chaotic measures like this quantum Lyapunov exponent and the butterfly velocity. And we know that this is true now in, I think, all QFTs that have a classical holographic dual, and people have also started studying this away from classical holographic duals, like in this SYK chain, and there's pole skipping there, but we don't quite know what it means, and so on and so forth. Okay, so I will stick to the theories where we do know what it means. Okay, so where we do know what it means, so for theories that are large n, they can even have perturbatively small inverse coupling, so they don't need to be at infinite coupling. What happens in such theories is that this dispersion relation, let's take the sound mode, the dispersion relation, which is here, and it has some coefficients that can depend on, I don't know, 700 chemical potentials, and I don't know, whatever you like. All of these dispersion relations will go through a predetermined point. So this curve will go to a predetermined point, which is determined by quantum chaos. All right. So the statement here is that omega as a function of q, which is imaginary, and it equals to I times lambda L over VB. Now, of course, in all these theories, lambda L is 2 pi t, but VB is non-trivial. So this will equal to I times lambda L, which is, incidentally also the first Matsubara frequency. So the way you find such a thing, it's associated with this behavior of a 0 over 0 in the associated retarded correlator that has this pole. So there's a pole, okay? And you can compute the residue of the pole, and you will find places where this residue is equal to 0. And the lowest such thing for positive imaginary q will give you exactly this pole skipping point, which will enable you to compute the butterfly velocity without actually computing the OTOC, right? Now, the reason for this from the point of view of field theory is not well understood actually at all. So the best understanding we have so far of this is from the point of view of this effective theory by Blake, Lee, and Liu. It's an effective theory of chaos, where if you take chaos as being dominated by some energy mode and so on, that's kind of a hydrodynamic mode, then you can predict this behavior. Now, we understand this very well from holography, and we know that the reason for this is triviality of Einstein's equations at the horizon. Okay. Now, what has also been shown by this work by us and by friends is that there's actually an infinite sequence of such modes. So this is actually a plot from this paper by Blake, Davison, and Weg, and this is it's an example of some correlator. It doesn't only happen in sound mode. There's these various pole skipping points all over the place, and a lot has actually been done on this. So we understand this now fairly well, I would say, in classical holographic theories. Okay, so the point here is that these dispersion relations have a specific point through which they like to go. All right, this is and it's predetermined by quantum chaos. Okay, so now I will use this in order to also implement some bounds that I'm about to sort of start discussing now. So is there any question about this before I go on to the business of univalence? Now I'll get some water. Okay, I guess this is sort of, there have been talks, some very nice talks about this holotube, so I guess this is fairly clear to most of you. All right, so what now? So we have these sort of this, golden standard bound type by Maldacena, Schenker, and Stanford, which is an exact bound that is actually saturated by models, all right? So this is a bound on the Lyapunov exponent. We also have an exact bound on weak quantum chaos, all right? Now, there's a huge number of various bounds that have been discussed, not on quantum chaos, but on transport. And these bounds have been very important, very influential, and they have really sort of stimulated the discussion in the field to a great degree. So for example, we have this famous relaxation time bound by Sachdev. There's the KSS bound on shear viscosity and sort of, amendments of these various things. And then we have these bounds on diffusion, a la Hartnell, and then Blake in relation to butterfly velocity and Lyapunov exponent. And there's also this beautiful bound on the speed of sound, which is, that in some families of theories, at least, there's an upper bound on the speed of sound, which is the conformal value. And we know that actually, if this were true, and it's probably true in some cases, this has important consequences for the phase diagram of QCD, okay? So what I want to do now is I want to find these types of bounds on transport, but with precision of exact inequalities. Because of course, while these are sort of, extremely sort of stimulating and motivating, it's very, very hard to make such things precise. And we know that there are always sort of counterexamples to these things. So what I would, simply like to do is to understand whether we can come up with some analytic structure that will, at least for some classes of theories, make bounds of this type exact, right? Now, I should say here, these chaos bounds actually come from, various mathematical properties of underlying theories. So in particular, this exponential Lyapunov exponent bound, this comes from essentially, some statement about the analytic structure of the OTOC and a very simple theorem of complex analysis. So this is more the kind of thing that I would like to do now, okay? And I stress that this need not be universal, all right? I will make no claims about universality. I just want to introduce a new set of methods where these types of bounds can be made exact, all right? Now, this is, for those of you who were sort of following this business of dirty metals and incoherent transport and its various sort of nice things, these are sort of closer in spirit to the exact bounds of the type that we discussed in the past on conductivities and so on, in the sense that they're exact, but they're not universal, okay? So they're not really of the kind, because that was more physics motivated. And what I want to do here is I want to, introduce a layer of mathematics which will enable us to make precise statements. And this, this was sort of introduced in this PRL of mine. And, I want to tell you sort of what is the status of this now, and then I will tell you what are the outstanding problems. I will be sort of complaining about this throughout, and I will try to tell you as clearly as possible what I think are the missing pieces of this, okay? All right. So, all right. Let's start with some mathematics. So the whole thing relies on the theory of what are called univalent functions. So what is a univalent function? Well, it's a function, all right, f of z, where z, so z is of course in the complex plane. I will be doing complex analysis. And this function is complex, all right? It's holomorphic. So this means that at least in some region, it's analytic, right? I don't want them to be globally holomorphic, so they need not be entire. That's the word that people use. So they're holomorphic in some region. And crucially, this is a new thing, they have to be injective. So what injectivity means, to remind you, it means that f of z of 1 is not equal to f of z of 2 for all z1 not equal to z2, in the region of this holomorphicity at least, okay? So what this means is that it maps in sort of one-to-one, all right? This is somehow the phrase that people like to use. It's a one-to-one function. So it's holomorphic, it's one-to-one, it's complex, but it doesn't have to be necessarily invertible, okay? So it doesn't have to be bijective. It's enough if it's just injective. Of course, if it's bijective, then that's even nicer. So, all right, now let's imagine that we have such a function. And it's univalent in the complex z plane. It's univalent in some potato. Let's call it U, all right? So there's some shaded region U where this is univalent. Now, this is all nice. So what you can do, you can use the Riemann mapping theorem, and any such region can always be mapped to a unit disk via a conformal map, all right? So I can take my zeta, I go from z plane to zeta plane, and my zeta is some function phi of z, which is, it's invertible, it's holomorphic, it's all nice, and its inverse is also invertible and holomorphic. So this is a conformal map. So z is equal to phi inverse of zeta, all right? Now I go to the zeta plane, and I do this in such a way that I map U to a unit disk. A unit disk is, defined as zeta such that the absolute value of zeta is less than 1. This is an open unit disk. I do not include the boundary, okay? I'm talking about open regions. All right, good. Now, of course, such a function in the zeta plane has a power series representation, all right? F of z is some power series representation. It's analytic, so it's guaranteed to converge everywhere on the open unit disk. And I can always normalize this function in such a way that this function is 0 at 0 and its first derivative is 1, okay? These functions are called univalent functions because they're normalized in such a way, they're usually called schlicht functions. In German, they're simple functions, all right? Now, if you thought that holomorphic functions were stiff, right? So holomorphic functions, that they cannot grow with arbitrary rate. For example, this whole business of the Maldacena-Schenker-Stanford bound is a statement of how fast a holomorphic function can grow when it's mapping from a disk to a disk. Okay, so this goes under this, I don't know, Schwarz theorem and Pick-Schwarz lemma, and they're various incarnations of the same thing. Okay, and some bounds on hyperbolic geometry and things like this. So these univalent functions are even stiffer. All right, they have very, very restrictive properties. So all you need to have is a function that's injective, all right? And then it becomes very stiff. So in particular, there's something called the growth theorem. So when I'm working after my mapping, when I'm working in the zeta plane, it's a theorem that the size of the function of f of zeta is bounded both from below and above at every point, okay? So it's bounded from below by zeta over 1 plus zeta squared, and above by zeta over 1 minus zeta squared, all right? Now, there's an even more fascinating statement, which is called the Bieberbach conjecture. So it was a Bieberbach conjecture from 1916, And it was finally proven by a French-American mathematician, de Branges, in 1985. And it's actually, it turns out that for such functions that only have this specific property, you can show an inequality on every single coefficient of this series. So basically every coefficient, Bn, has to be bounded from above by n and from below by minus n, all right? And this is true for all n greater than equal to 2. So you can see this is, so you can sort of see where I'm going, right? So this constrains every single coefficient of a holomorphic and injective function that has a power series representation on the disk. Good. So there's an extremal function that satisfies all of these inequalities, and it actually saturates them. So all of these inequalities are saturated by some function, and it's called the KOEBE function. So this KOEBE function is, well, it's just defined as this, is zeta over 1 minus zeta squared. So this has a power series representation, which is zeta plus 2 zeta squared plus 3 zeta cubed, and so on. All right, so you can sort of, you can see why it saturates the Bieberbach conjecture. It also saturates all of the other inequalities in this vast theory of univalent functions. So it's a nice function. So it has another actually very nice property, is that it conformally actually maps a complex plane to, it maps a disk to the complex plane without a cut, all right? So this function maps D to C without a line from minus infinity to minus a quarter, all right? So this is actually related to another very famous theorem, which is called the KOEBE 1/4 theorem, which was proven by Bieberbach. So this is all, sort of kind of the same people, which has also a fascinating statement, which I think will be important in the future, but not for today. And the statement is that any univalent function mapping D to C contains a disk of radius 1/4 around the origin, okay? So basically, this kind of a function always maps to something that has an analytic disk, which has a radius of 1/4, right? Okay, so these functions, as I say, they have very nice properties. Now, the question is, when is the function univalent, all right? Of course, not every function is univalent. So there's a sort of an easy way to define local univalence. So a function is locally univalent if it's, if it's invertible at a point. So by this implicit function theorem and so on, you can see that local univalence at every point is ensured if the derivative of f is not equal to 0. But it's not sufficient to have global univalence. So proving global univalence in the whole region is very tricky. And this is the sort of the main, obstacle to making, or has been to making generic statements about the kind of thing that I'm going to talk to you about. So there's a sort of a very, very long list of sufficient and necessary conditions on univalence. And there are hundreds of these conditions, and you have to sort of plow through them and choose whatever fits you, because some are good for some, others are good for other things. So one particularly nice univalence condition can be actually stated in terms of the Schwarzian. So this is the definition of the Schwarzian derivative. And you know that Schwarzian derivatives play a sort of a deep role in the theory of conformal maps. So f of z, for example, is univalent if the Schwarzian derivative of this function satisfies an inequality of this type, okay? But if f of z is univalent, then the Schwarzian derivative is bounded by 2 being replaced by 6, okay? So there are these kinds of statements that you have to take into account. Now, I will not work with the Schwarzian derivatives because I don't know what is the physical meaning of a Schwarzian derivative of a dispersion relation. Maybe there is some deep meaning to this, I don't know what it is. So for me, the most convenient condition is to actually have the real part of the derivative of this function being positive in any convex region. All right, so if you can prove that the real part of your derivative, this was the local part, this is now the global part, if this is true, then your function is univalent everywhere where this is satisfied. Now, actually, then you can do, of course, then you can do the Riemann mapping theorem, you map to a disk, and you can show, if you can then show that the real part of the derivative after the map is still positive, then your functions will satisfy even stronger bounds that are due to McGregor, okay? So basically you get a modification of this growth theorem, which I had here, and modification of the Bieberbach conjecture, which is a theorem, not a conjecture. And so you can see why this is stronger. Let's not look at the first line because it has some logs, just believe me, it's a stronger bound. So for the series, you can see why this is stronger. It's because before Bn was bounded by n, and now it's bounded by 2 over n, okay? So it becomes more and more and more restrictive at higher and higher orders. All right, good. So this was mathematics. Now, what does this have to do with hydrodynamics? So let's look at our series, right? So we have some kind of diffusive series. This is the diffusive series. And the first coefficient of the series is the diffusion constant. We also have the sound series, which has this form of the Puiseux series. And the first coefficient is the speed of sound, okay? So basically one can do the same thing to both types of series, but let's just focus on diffusion for some reason. So it's easy actually to see that a diffusive dispersion relation and the sound dispersion relation will always have a finite region of univalence. So it's very easy to see this. So at the origin, they're univalent because they're Puiseux series. They're sort of analytic at the point. And then it's easy to show that actually this kind of a function will always satisfy this condition, at least for a finite regime of z, okay, where z here is q squared. All right, I'm working in the variable where z is equal to q squared. So for sound, it's actually more convenient to work with z being equal to square root of q squared, but let's forget about sound for now. Let's just focus on diffusion. So, all right, so what am I going to do now? Now let me define a function f, which is I times omega, right? I'm just defining I times omega, I can do this. And then I map this thing to a zeta plane, all right? So I can then define f of zeta, where this is equal to I times omega of diff. This is this diffusive function, right? The dispersion relation. It's a function of z. So z is the inverse map from the zeta plane. And I'm normalizing it in the way that my Schlicht univalent functions are normalized, such that the first coefficient is 1. All right. So this is done by dividing out the diffusion constant and the value of the conformal map at the origin. Good. Now, this is then the situation, right? So I have in the original z plane, which is the q squared plane, I have a univalent function. And let me now also assume that I know the value of this dispersion relation at one point, only at one point, which I call z0. Then I can do this conformal map where I map, it has to be done in such a way that 0 is mapped to 0 for technical reasons. But I can then map this to a unit disk in the zeta plane, where of course I also know the function, the function at the value of zeta 0, which is the conformal map of z0. All right, I still know the value of the function. I only changed the domain, I didn't change the function. Okay, so let's assume you know this. So as long as you know this, now you can actually prove exact and rigorous bounds on every single coefficient of the hydrodynamic series. They follow immediately from the theory of univalent function. In fact, so what you do is first you bound diffusion. You do this by using the growth theorem, and it's completely bounded by only the knowledge of the function at one point and the conformal map. So of course, to know the conformal map, you have to know the region U, right? So you have to know the shape of the potato, all right? But as long as you, let's say you know this, then you can map it to a disk via a known conformal function. You always know this can be some kind of Mobius transformation or, I don't know, Schwarz-Christoffel or something like this. And you can prove, you can bound the diffusion constant from below and above. You're done. Now, once you've done this, this conformal map reshuffles the coefficients of the series, but each coefficient of this new reshuffled series, which is done in, in a nice way, is bounded by the Bieberbach conjecture. So you can also then prove a bound by using Bieberbach on every single coefficient of the series. And even stronger bounds follow, as I said, if the real part of f prime in the new zeta plane is bounded. Then you get these longs, okay? Fine. So the question, are these hydrodynamic dispersion relations really univalent? The answer is yes, they are. They're generically univalent. It's because they're holomorphic and invertible as z equals to 0 by Puiseux, so they're locally univalent, and then it's easy to see that they will be globally univalent, at least in some region. And I can, invent some conditions on this kind of stuff, which are not particularly physically intuitive, but you can sort of imagine, basically something goes wrong when the real part of f prime stops being positive. So f prime is roughly related to the derivative of the dispersion relation, and this is related to the group velocity. So I can write down some conditions on the group velocity whereby, basically my thing will stop being univalent when I reach that value of the group velocity. Now, what actually happens thankfully, in these examples that I will look at is that they are univalent, at least for diffusion, just everywhere on the disk where they are actually convergent. So, this condition where I would lose univalence happens somewhere outside of the disk, so I don't have to worry about this, okay? So this happens for diffusion, and for sound, what actually seems to happen, and I don't have a generic proof that this is the case, this is still missing in this business, is that sound seems to die, the univalence of sound seems to die where the local condition is violated. So it happens somewhere that the group velocity in the complexified momentum space is 0, and at that point you lose local univalence, and therefore you lose, global univalence as well. Now, if you don't do anything, if you don't use any brain power at all, you can just use these inequalities, and you can push the known point to the edge. Okay, that's sort of the worst that you can do. And what you get then are some immediate bounds. Okay, so immediately you can show that diffusion must be bounded by 0. Okay, this is good because this is entropy and so on. And the upper bound is 4 times something written in terms of the phase velocity where the univalence dies. Okay, so you get this kind of an expression, and for sound you get something analogous. All right, now this q bar here is the minimal value of either this group velocity condition where I lose univalence, or the critical point where I lose holomorphicity. All right, so here I'm restricting myself to these disks because this is easier. Of course, you don't have to have a disk, right? So you can have the death of analyticity somewhere in the complex plane, but you will still have a univalent function around. Now I will show you such an example. But you can already, without sort of essentially knowing anything, you can make some statements about bounds on the diffusion constant in terms of the phase velocity, for example. Okay. Now, you can also go and look at explicit holographic examples and see what is going on. So what I looked at was diffusion in n equals to 4 super Young Mills. And then lo and behold, well, okay, so they're convergent, right? So they have nice analyticity properties up to the radius of convergence, great. One can also check that actually this group velocity is not a problem. So such functions, at least for these neutral theories, and again, I don't have a proof of this, so this is a problem. But for example, for n equals to 4, for M2 theory, and these kinds of simple holographic cases, it seems that they always have nice univalence properties everywhere on the disk of convergence. Now, which point am I going to pick where I know the function? Well, I'm going to pick the pole skipping point because that's actually easy to compute from holography. All right. Then I use this machinery and I just plug it into the, I check that everything's okay, and I plug it into the bounds. And here actually one can use these more stringent bounds with the logs because they have even nicer sort of univalence properties, and you get the kind of bounds that I'm stating here. So you get a lower bound on the diffusion constant, which is something not too bad. The actual value is this Polycastro-Son-Starinets value of 1 over 4 pi. This is 0.08, and the upper bound is 0.2. Okay, so you get within reasonable orders of magnitude bounds on these coefficients, and then you can actually directly also show an inequality for every single other coefficient, even if you didn't know what these were, right? So you get them bounded from above and from below, and you can see actually intuitively the better the convergence property, the bigger the radius of convergence, the more squeezed the higher and higher coefficients are. Okay, now let me show you the simplest sort of the maximal univalent example. Let's do the following thing. Now let's assume that my dispersion relation is univalent everywhere. Okay, why not? It's univalent everywhere except at the single branch point. So this means that there's a branch cut, okay, but everywhere else it's univalent. So it looks like this, right? So there's a radius of convergence, and an example of such a thing is this self-dual axion model, which was solved by Richard and Blaise. And they show that this dispersion relation of the diffusive mode has this simple form. And this is indeed univalent everywhere, except at the cut. So then actually one can use this business for all of the theories that fall into this class of analyticity properties. Then I can prove that in general, you can use actually this KOEBE function to map to a disk. And what you get with the pole skipping in place, you get some very nice bounds that are actually exactly of the type that were proposed by Mike Blake before, right? So recall this. The type of bound on diffusion was VB squared over lambda L with some number here. So if your quantum field theory has this particular property of univalence, then you can show that for energy diffusion with pole skipping, there's a lower bound, which is exactly this VB squared over lambda L, and there's an upper bound, which is VB squared over L plus lambda L over R, where R is the radius of convergence. Again, okay? It's the size of this disk. And if you have momentum diffusion, then you have a lower bound, which is more non-trivial, and upper bound, which actually has this Blake-like value. Okay, now you can then also find bounds on every single other coefficient, and in particular for such theories, the second coefficient has to be positive and it's bounded from above by d over r. And I think there's some interesting connection to recent work by Wu, Baggioli, and Lee in terms of this positivity of C2. Okay, but I will not discuss this. So what you can see again is if the radius of convergence is improved, then your series is squeezed down. So basically you kill all of the higher terms and you only preserve the diffusive term. So basically your omega becomes exactly minus I dq squared, where d is precisely determined by this VB squared over lambda L. And this now follows from pulse skipping and just analyticity properties. Okay? All right, good. So for sound, one can do similar things. And as I told you, it seems that that univalence of sound dies with this local condition. Now, again, there's a question mark here. I do not have a proof that this will be true generically, but one can actually, in this case, approximate the position if, you know, because this happens within the disk of convergence. This means that this point actually, you know, you can use the hydrodynamic series. It will converge to this point. So you can have an exact numerical estimate of where this happens. It happens here. This is the first line. And you can have a hydrodynamic first order approximation to this. And then you can use this. You can actually use hydrodynamics to constrain hydrodynamics, right? You use itself to constrain higher coefficients. So you can do such things, and you can get some bounds on sound in the same way as for diffusion, okay? Now, what is actually particularly interesting for sound is that one can construct a sufficient analyticity condition on the dispersion relation such that if it's satisfied, then all of the theories will immediately obey the conformal bound, okay? Now, it's stated in terms of this conformal map from Z to zeta. I don't have any idea what this means intuitively, but it's an analytic condition that if this is true, then, you know, your VS for all of those theories will be bounded from below by 0 and from above by 1/3. And obviously, this needs to be investigated. It needs to be investigated in examples where the bound is actually obeyed. But of course, we know that, you know, there are many examples where it's actually not obeyed. So we need to see whether, you know, this condition is violated and how this works. And actually, I found something, I think, that is better, that I'm able to prove more generically when this is true. But so, you know, you should stay tuned. So, you know, this is sort of work in progress. But I can sort of do new things that are not in this paper, and I will also not discuss them here. But, you know, I think there's sort of a lot to be done here. So what is the summary? So the summary is that the complex analytic structure of transport, okay, reveals, you know, very nice new physical properties. And secondly, of course, this doesn't have to be sort of promoted in this holotube business, but holographic duality is actually an invaluable tool for exploring QFTs. Okay, so I think we all believe this. So the first part was to convince you that hydrodynamics has exceptional analytic convergence properties. Okay, it converges very nicely. Now, again, the statement of convergence is generic, coming just from hydrodynamics. To check what actually the radius is, you need a model, right? So then we have this holographic input, right? And no, we can hope that generically this will be true for all strongly coupled theories. You know, there's some principle of optimism happening here. Now, for pulse skipping, it's a precise analytic relation between hydrodynamics and quantum chaos, which is, you know, of the kind of thing that people have been searching probably for many years. And it's exact, right? So it's not something with wiggly lines. It's not something that, you know, these kind of estimates of disks colliding, of Lorentz gas and all this kind of stuff, you know, this is sort of intuitively important, but it is not mathematically exact. So at least for holographic theories, we now know for, you know, for this set of large N holographic theories, we now, at least for those theories, we know what is the relation analytically between hydrodynamics and quantum chaos. And sort of lastly, the main part of what I wanted to do today was to show you a new set of methods, okay, from the field of complex analysis, which is a promotion of this field of holomorphic analytic function to the theory of univalent functions, which actually allows you to put rigorous and exact bounds on every single coefficient of these hydrodynamic dispersion relations, including on the first term, which is, of course, the most interesting one, right? So one can actually have a tool to prove exact bounds on diffusion and speed of sound, and I showed you some examples. And you can apply them again to holography. You can make generic statements in terms of some group velocities, phase velocities, and obviously this needs to be better understood. Like, you know, it needs to be understood better beyond a set of mathematical tools to really sort of nail down what is the physical meaning of all this and what can be generically said. And this is sort of the first thing to be done, right? We need generic results. We need to understand this sort of better. And I already understand some of these things, so you know, stay tuned. But I think there are multiple things to be done. And, you know, what are the applications? And then, of course, there's the uninsightful comment of we need to apply this to not large n. Of course, ideally, we would like to understand if say the speed of sound is bounded by something in all asymptotically free theories like QCD and things like this, and then to this recent beautiful work by Alexei Vorinen and Kurkela and collaborators, better understand whether this has something to do with free quarks in the cores of neutron stars and so on. This is kind of the goal, and better understood diffusion bounds for incoherent transport and various things like that. So I hope that there will be some place for all this in the future. But for now, I just wanted to show you this sort of new set of methods that I don't think was used anywhere before. So there's actually I had no idea about this when I was writing this, but it does turn out that there does exist one paper. I think maybe there are more, but sort of recent explorations have shown that there is a paper from 1965 by Kuri and Kinoshita, where they started actually using these methods to put bounds on scattering amplitudes in quantum field theories. And if you think about it, of course, the problem of finding bounds on scattering amplitudes is kind of exactly analogous to what I'm doing here, right? So you have some upper lower bound on your scattering amplitude, and let's say what you want to do then is figure out from this what are the bounds on coefficients of the series of an effective theory that reproduces such a scattering bound. And actually, this March, there's a new paper that appeared from an Indian group of Aninda Sinha and collaborators, where they actually started using these methods now and actually precisely applying them more carefully to this business of scattering amplitude. So in March, there was this paper called Quantum Field Theory and the Bieberbach Conjecture, which I would also sort of encourage people to look at. And hopefully, with this new set of methods, we can now do something. Ideally, there won't be a next 60, 70 years where nobody writes a paper about this. And, we can hope that from the point of view of hydrodynamics, we will find new things. From the point of view of generic effective theories, because, after all, these are all effective field theories. So, maybe we can say something about QCD and so on and so forth. So thank you very much for your, for your attention. And I'm happy to answer questions if I know how to answer them. Thanks.
Thank you very much for this very, very interesting talk, Sasha. Any questions? I can start. I have a few. So I'm wondering about the comparison of the bounds that you derive using the univalence and properties of the well, also of the conformal maps that you're using. How those are related to the bounds that we know of, like, for example, analyticity of the hydrodynamic two-point functions, which tell us there should be positive shear viscosity, for example, or like you can also alternatively look at the entropy current argument, right? So we get inequalities from those. However, the bounds that you see here or derive are more stringent in the examples that you've shown us, right? So instead of just being larger or equal to 0, the shear viscosity, I understand in the one example at least that you've shown has to be larger than a certain number, a positive number, right?
Yes. So, I mean, this is a great set of questions of the kind of things that I would like to understand. So I do not, so there are these bounds, there are constraints on analyticity of Green's functions. I don't quite know how to translate those into properties of dispersion relations, because here I'm talking about the analytic structure of dispersion relations. And some of these analytic structures that I think maybe seemed obvious are actually wrong. Things like boundedness of the group velocity. It doesn't actually have to be bounded by 1. So there are various things I think that are floating in the literature, which are usually correct, but not quite correct, actually. So I think this has to be better understood. I do not know what is the relation to this analyticity of the Green's functions. I would like to know. Now, you mentioned this. So typically these entropy constraints are very weak, right? They only say D is greater or equal to 0. They don't really say much. So these are, for all these cases that I have looked at, they're compatible. There's nothing that's incompatible with these. But these are much more stringent. I mean, they're upper and lower, and yeah, they're typically this is much more restrictive. I mean, but they don't violate any entropy bound that I would be aware of. Yeah, so somehow we need to understand better this generic, somehow physical intuition into dispersion relations. I think that's kind of missing. And yeah, okay, so we know that the phase velocity has to be bounded by 1. The group velocity does not have to be bounded by 1. And in fact, it is not bounded by 1. And for example, we see explicit examples of this. I mean, but you take n equals to 4 diffusion, you keep momentum real, and you make it large, and this diffusive dispersion relation goes as q to the 4. This happens also for M2 brane. There's this recent, also very nice example for this axion that Richard and Blaise and other people who may be here had. They also had, you can look at asymptotic. So, then the group velocity will scale as q cubed or something like this. But it's only because it's imaginary. So, I think there's some better understanding is required. And it would be ideal, of course, if we could relate this, pin it down to the kind of analyticity we know correlation functions have to obey, right? Yeah, so I think this is, it's very important, but I cannot really answer it at the moment.
I see that Umut has a question, but let me just tag on a comment on that. So it seems to me that the analyticity properties are encoded in the spectral curve, which you can think of as the inverse of the Green's function in momentum space. And so it seems like there must be a relation there. If you choose a particular potato, as you called it, right? If you choose a particular univalence region U, so that's, I mean, my hunch, but just, I don't know if that's correct. I just wanted to.
Yeah, I agree. I think, that's right. So the spectral curves, they should know something about the asymptotics and being related to the factorized solution somehow. So I think there's this additional theory which I was able to use now to make some progress, but this is still mathematics. So there's physics missing here. Yeah, I completely agree. I don't know if anyone said it. You're probably all thinking it, so I agree with you.
Maybe Umut is about to say something along those lines.
No, I have no wisdom. Well, at least not at this hour, not today. So no, okay, I actually have a very stupid question. So so everything depends on the assumption of univalence, of course.
Yes.
And you said in the example that you showed that can you repeat how do you prove that these functions are univalent, at least in some region?
Yeah, so okay, so let's see, how should I say this? Do you still see my screen, or did it stop?
No, we see it.
You see? Okay,
yeah.
But it's just smaller, right? It's not full screen. Right, so basically, you know that the dispersion relation is analytic, okay? It's analytic. This means that it has a non-zero derivative at 0, okay? D omega by dq at q equals to 0 is non-zero.
No, I understand, but it can turn back, right? So like it doesn't have to be injective after. So you're saying when it goes back, this is the end of this is the bound you put on your.
Yeah, that's right.
So then I see.
So the point is that it starts. So if you want to think of it, this real part of f prime of 0. Where did I have this condition? So this thing, right?
Right.
So at z equal to 0, this starts at 1.
Yes.
So it always takes it at least a finite time to come to 0. This is what happens. So let me show you this plot. This is what generically happens. So, okay, so this is now the plot of the real part of f prime after I map to the disk. Doesn't matter. So I'm looking at real part of f prime of zeta. Okay. Now I am going to, the x-axis is, so I take my zeta and I complexify it. I make absolute value zeta e to the I5, and then I verify along the circle, right? So red is zeta equals to 0. So you always start with this function at 1. And then different colors, I go from red to blue as I'm varying the absolute value from 0 to actually the full disk of convergence. And so this, at least here generically, this goes up. You can show this at least for some region, but it always takes a finite a finite absolute value zeta for these functions to be able to reach down to 0. This is very easy to see. So they do for sound, they reach 0. So this is the same plot for n equals to 4 super Yang-Mills sound. Again, you start at 1, okay? So it's, you start at 1, then you vary the parameter. And because this is an analytic function, it will take it a finite time as you vary zeta to come down to 0. Now, for sound, it comes down to 0. And actually, there's also a reason why this is 3 pi over 2. It comes to 0 exactly when the group velocity is 0, okay? So this is why you see that there's always, so the statement is that they're always univalent, so you can always use these methods. The question is, how big is the regime of univalence?
Right, right, I understand. So I was, no, that's good. But so I was just hinting at maybe some perturbative quantum field theory. So assume, so you can also do calculations in perturbatively, right? So you can, assuming that, say PQCD or something like that, assuming that hydrodynamic approximation is valid, which, there can be some kind of a perturbative regime where it is valid. Then, not for QCD maybe, but for other theories probably. Then can you see if this univalence arguments also would hold, beyond strong coupling? Large N is a different question, but like I was more into,
I think so, yes. I don't see why they wouldn't. So as long as there's not some weirdness of a branch cut in the dispersion relation happening, or something that I don't understand, because we don't really know what is hydrodynamics at finite n, so let's leave that. I think coupling is not an issue. So they will, if you go to finite coupling n equals to 4, this kind of stuff, that will still have nice analyticity properties. For perturbation theory, it's hard to say. So because it doesn't have to be analytic in the coupling, it has to be analytic in the dispersion relation. So, the fact that I think that but maybe I'm I'm jumping the gun here.
No, that's right. But what I was, but it may be that as the coupling constant goes to 0, these bounds shrink, right? So it can be, for example, so this thing that I see here in the for the diffusion coefficient. So that's, for example, in the shear viscosity, of course, that it goes to it diverges, right? So it perturbative. So in that case, for example, I don't know if there is any kind of clash between this kind of statement and
because they go with 1 over r. So the radius of convergence goes to 0. The upper bound generically starts exploding.
Okay.
That's what happens.
I see. So you would still expect that all of these arguments to be
I would. So let me do you see this thing?
Yes.
So this is the simplest example of univalence. So the dispersion relation is by assumption univalent everywhere. It's univalent everywhere except at this red cut here, okay? And this happens because, so the dispersion relation has a finite radius of convergence, okay? But by analytic continuation, so univalence can be larger than the radius of convergence. Maybe I didn't stress this, but this can easily happen, right? Because the radius of convergence is only about the statement about the analyticity of the series representation. But so this example will be convergent only in the green disk, but you can analytically extend, so there's no problem. This is an analytic function everywhere except at the cut. So you can also see here, for example, explicitly, forget about this butterfly velocity, whatever. It's just some point. You can see here that the upper bound, for example, in such a case, will go with 1 over r. So the upper bound for diffusion goes to infinity as the radius of convergence goes to 0, which is what you would expect at weak coupling. So I think, as far as I understand, it's consistent with going to finite coupling. I don't know about n.
it ceases to be useful, but indeed, so right, I see.
Yeah, so I mean, I guess eta over S blows up. So yeah.
Okay.
So I guess that
okay, but you can also have some disjoint neighborhoods of univalence, right? So you can
Yes.
have different islands of univalence, which would that put some extra constraints, or do you think how would that work out?
It can, yeah, you can put, I mean, let's say you have a dispersion relation, you put some bound here, and then it's not univalent in some region, but it is holomorphic into that region, then you can put some bound again there and maybe combine them. Right. I haven't done any such examples, but I can easily see how this would work. And I should say that this, this doesn't have to be applied to gapless modes. You can just subtract off the gap and just then do it again. It's a very generic tool for anything. That so yeah.
Okay. Yeah. Thanks
so much.
Okay, Matthias, can I ask you a question?
Yes, of course.
Okay, thanks. Sasha, thanks for the talk. I have a question about the applicability of your method to the case in which the pole skipping point is not within the domain of convergence of hydrodynamic derivative expansion. Mm-hmm. I think my question somehow is related to the previous discussion. For example, in the graviton axial model, we already know that the pole skipping point is beyond this regime.
Yeah.
So
so I don't even have to change the slide here. Yeah, let's go on.
Yeah, yes. So from your statements, I understand that we are still allowed to use this method just by doing analytic continuation.
Yes.
So
right.
You mean so it is not needed the pole skipping point to be located within the domain of convergence? No,
it doesn't have to be. It's just more convenient.
Okay.
So this is exactly. I mean, this Davison-Goudreau solution, which I have here. This is exactly what you're mentioning, right? So here, the radius of convergence is green, but for their specific example, it's its translational symmetry is broken. So what they have is energy diffusion. So energy diffusion has pole skipping point, which is here. It's outside of the radius of convergence. So the series doesn't converge, but its analytic continuation is holomorphic everywhere except along the cut, and it's also univalent everywhere. So you can just use it. So you don't have to. Yeah. So it extends beyond the series as long as you can do the analytic continuation. Of course, nobody's saying that this is easy, but the method is not limited to the fact that you need to know a point inside of the convergence radius, as long as univalence spreads out over the convergence disk. Yeah, and here too, I mean, so for example, also for this diffusive business in n equals to 4, so here I only look at the disk because it's easier, and mapping disks to disk is easy because you can use Mobius transformations, but this thing is still univalent outside. It's univalent more than just on the disk of convergence. So for example, one of the questions is, what are the optimal bounds? Can one prove optimal bounds? In general, I don't know how, except in this case. I very strongly believe that this is an optimal bound because the mapping can be done by the KOEBE function, which extremizes all of the inequalities in the theory of univalent inequalities. Yeah, that's a very good question. Yeah, thanks. Did I answer? I don't know if I can say more because I don't know more.
Thank you. Thanks.
Are there more questions? Maybe we're running kind of out of time, but people are still here.
Yeah, time.
Well, maybe a comment or a thought more that might be wrong on Umut's question and discussion. At finite n, there would normally be like a continuum, right, in the spectrum. So there would be a branch cut in the dispersion relation in that sense, which you said you feared might destroy some of this,
or at least make it worse.
Yeah.
So it's okay. I mean, I also have, there are also cuts because of level crossing. But I mean, otherwise they can also, those cuts. The 1/n cuts, I don't understand. But yeah, they're probably there. I mean, the question is, where do they end? If they end at 0, then maybe you have to be very creative with univalence outside of any disk. Maybe you have to go into the upper half plane. Maybe there's something to do with analyticity of Green's function. I don't know.
Also, in critical cases like the Reisner-Nordstrom extremal, I mean Reisner-Nordstrom extremal or Myers-Perry extremal black holes or brains, you would have branch cuts appearing. So
yes, yeah,
those might be interesting cases to study to just understand.
Yeah, definitely. Yeah, for example, this I mean, Richard is still here, I guess. This thing that they were studying, that's what I was mentioning with Blaise, they have this very nice, actually analytic, control over this limit. So maybe something like that would be good to understand. Yeah.
But why would you be so afraid of the branch cuts? I mean, can't you just go to the multi-sheet description and try to have univalence there?
Yeah, you can. I'm not that afraid of it. I'm just saying that I don't know what is hydrodynamics at finite n. But I can deal. I mean, I can deal with univalence theory on Riemann surfaces. That there is such a thing. Yeah. So you're right, Umut. There's no reason to panic. That's right. I mean, they can be nicely univalent just on different sheets, and you can still do things. Yeah, you're right.
Are there any more questions or comments? Otherwise, we would close the official part. Right, which seems to be the case. So thanks again, Saso, and thanks everyone for contributing questions and comments. I'll see you next week. And